So welcome to yet another crazy integral that can't be solved with normal techniques. So what do? We go to complex numbers, of course. So the thing is, this can be written as the real part of the integral from 0 to 2 pi e power cosine x and then e power I sine x dx, right? And then you can actually do this thing, but then cosine x plus I sine x, that sounds very familiar, doesn't it? This thing is just the real part of integration from 0 to 2 pi of e power ix dx. But now the question is, how do we even solve this thing? Is this even solvable? You might think that, okay, maybe we can do some kind of substitution, that maybe we can do this like, so this integral we can do it like integration from 0 to 2 pi of e power ix, and then you got I e power ix dx, but now you have to divide by that thing, so upon I e power ix. Now this whole thing is just d of e power ix. So you might say, okay, it's like integration of e power z dz upon, so I times z, I guess, right? But then x was going from 0 to 2 pi. What's z going from? You might say that z is actually going from 1 to 1, but then you might think, okay, this integral must be 0. But then remember that this actually is not 0. E power cosine x is always positive. Sin x goes from negative 1 to 1. So cosine of that thing, that has to be positive. It's in the either in the first quadrant or in the fourth quadrant. So this integral must be positive. It cannot be 0. This is of course incorrect. The thing is, complex integrals aren't so straightforward. So instead of doing it as a normal integral, you have to think of it as a path integral, because we are talking about 2D space. So this is like integration across a circle. So this is the circle we're talking about. So z goes on a unit circle. It starts off over here and then it goes like this, and then throughout this motion we are trying to integrate this thing, e power z dz upon iz. Now you can see why this was not such a good idea to convert this into this kind of function, right? Because once again we are just stuck at this thing. How do we do this? So there's another method that you can use. Think about it. The way e power ix is defined is using the exponential function. So the thing is, the exponential function and the e power function, both of them are different. So e power x, we say that it's equal to the exponential of x, but these are defined in different ways. So the thing is, x of x, that's basically the Taylor series of e power x that we use for real numbers, but then extended to complex numbers as well. So then this is just 1 plus x upon 1, then plus x square upon 2 factorial, and so on, right? One thing to note is that this series, it converges no matter what thing you put in there. So then that means this thing is actually valid for all values of x, right? So yeah, I mean, you can just put e power ix inside and it will still work. So e power ix, that thing is basically 1 plus e power ix plus e power 2ix upon 2 factorial, and so on, right? Yeah, but the thing is, integration from 0 to 2 pi of a term like this, that's going to be 0, because this thing is basically cosine of ix plus I sine of ix, and then the individual integrations of these guys, that from 0 to 2 pi will of course be 0. And you can also think of it as a bunch of vectors originating from the origin, and then each having the same length, and then you're trying to add all of these up. So of course it's going to be equal to 0, right? Okay, that's understandable, I think. So this kind of term, it's of course going to give us 0, but then this kind of term as well gives us 0, because then you can, I mean, simply just substitute. You will just say 1 upon 2 integration of e power I of 2x and then d 2x. That's the integral that you will be dealing with. So this kind of integral is also 0, and then so on. So even for e power 3ix, the integral is going to be 0, and just keep on going like that. So all of these terms, they don't matter in the end. All that matters is this term. So of course it's just the integration from 0 to 2 pi of 1 dx, and that's going to be 2 pi. So it's the real part of 2 pi that we look for. So this whole integral, its answer is 2 pi. So you might say, okay, that's where it stops, right? That's where the video should stop because we got the answer. No, I'll tell you something else that you might never have thought of. So recently I was studying complex analysis. I know. I'm very young for that. I need not do that, right? But then what can I say? I'm just really curious. So sometimes I go off into strange lands. So yeah, I did complex analysis for a while. Let's just not say I did. I think it will be better to say I tried to do complex analysis. So the thing is, over there I learned some few tricks. What we have is, so this whole integration can be thought of as the loop integral of e power z dz upon iz, as I showed, and then the loop is of course this unit circle, right, containing the origin. But then if you think about it, I mean, you can of course use the Taylor series expansion of e power iz. So this thing just becomes 1 upon iota, and then the loop integral of 1 upon z plus z upon 1 factorial plus z upon, sorry, that's supposed to be z square. Okay, it's supposed to be 1 in that case. 1 upon z, 1 upon 1 factorial, and then z upon 2 factorial, and so on, right? And now a theorem from complex analysis says that the loop integration basically of functions of the form 1 upon, so I should not say that, of the form z power n, right? So this loop integral, so whenever you have a closed loop, the integral of this thing z power n, this will in fact be 0 whenever n is not equal to -1. So for n equal to 1, 2, 3, so on, maybe even 0, -2, -3, whatever. So these kind of things, they have this integral to be 0. But for integration of 1 upon z about a loop, and if this loop contains the origin, then you can write this integration as 2 pi I. If it doesn't contain the origin, then you can write it as 0 simply. But in this particular case, it is containing origin. So our loop actually contains origin, and of course all of this times dz. So all of this part, it doesn't matter. As we saw previously, this really didn't matter because in the end the integrals went to 0. But then this integral, it does matter. So this integration 1 upon z dz containing the origin, right, is going to be equal to 2 pi I, but then you want 1 upon I of that thing, so it's just going to be 2 pi, exactly what we got before. But this basically makes a new question, that what if your loop was not a circle, so would it still work? The thing is, yes, it would still work. So this thing works for any kind of loop that contains origin. So even if your loop was like this, right, this integration, right, so e power z upon iz dz, this integration would still be 2 pi. That's the thing. So yeah, that's what I wanted to say. Yeah, and I'll see you guys in the next video. And of course you can always do this thing. So e power z minus a, and then you got z minus a over here, and then z minus a over here. So z minus a, that just refers to this being shifted to this point, right? So now this is our new origin. That would also be 2 pi, this integration. Yeah, okay, that's it. So I'll see you guys in the next video. Bye.